Recording. Looks like we're recording. All right. So, before we begin, questions on anything? To this point, I know that we haven't really gone over anything yet, but okay. One of the changes that I think we'll make, I was thinking that we do. So I had to buy a bunch of more material for the materials, bunch of equipment for the materials 1 class. But I also bought a maturity reader and some maturity sensors. I think we'll actually look at maturity curves in here. So I don't know if you've heard me wax poetic about using maturity in concrete analysis, but I think it's something that we can do in here and understand what happens here. But we'll talk about it more later in the semester when we get closer. Cody's here, right? Yeah, I saw Cody. Zach is here. Okay. Colette, I just wanted to let you know there is an online section, so recording lectures unless you feel otherwise. You know what? I forgot to. Hopefully our markers hold out today. Okay, so off to a great start. So chapter 1, we're talking about properties of forces. Right? So we've all taken materials 1. We talk about forces in there. What is a force? Yeah, it's when we exert energy on an object, right? Good. Right, so when we get back to talking about physics, right, a bunch of different equations to model how a ball rolls down a hill. Right, but let's think about it when we're on a job site. How are we interacting with forces? What do we have to keep in mind? How can forces impact us on a job site? Maybe they don't. Forces don't interact on the job site? Weight. Okay, weight. Weight of what?
Structure, beam.
Okay. Weight of our structure. Or elements of our structure. Okay. What else? What's that? Wind. Got it? Okay, wind can certainly, is it a little bit, I don't know, I got here at 6 o'clock this morning. Is there any wind acting out there today?
Not as bad as it has been just the last couple days, but
it's kind of still out there today. But yeah, wind can absolutely play a factor. What else? What else is being exerted on the roof right now? Snow load, right? So we can have snow, we can have rain. Okay? What else?
Live load.
What are we talking about when we mean live loads?
That's things that come in the building, people,
Yeah.
furniture.
Yeah. And really we should think of anything not connected to the structural foot frame. It's going to be a live load. Okay? So you may also hear this described as transient usually people with PhDs will talk about transient loads versus live loads. Okay? Changes with time. What transient means. Same thing that live load means. Also, when we think about the weight of our structure or elements of our structure, that's what we refer to as our dead loads. Okay, so those are always going to be there, always in place. Okay, so forces are always going to be interacting on our building. And the goal of the design is to create a concept of static equilibrium. Remember how to spell it. Okay? What's static equilibrium mean?
Nothing changes.
It's not changing. So the sum of all our forces equals 0. If the sum of all our forces equals 0, what happens to our structure? All good. It's going to stay in place, right? The walls don't tip over. The ceiling doesn't fall in on us, making a viral video. Okay? This is typically what we want when we're working in the construction world. Obviously not what we're building, but once we turn over the building. Okay? There may be elements that we want moving, but usually we want this building to stay in place. Okay? So how we model it is through mechanical force. Okay, a little bit different than the force that you can see when you go to Star Wars right now, right? Where F equals some mass of an object times acceleration. Okay? So, what does that mean for our units? What are we going to have for our units? Grams or pounds? What about acceleration?
Meters squared per second.
Meters squared per second. Yep. Yep. Okay. So if we were doing a classical, we're doing a statics class based on classical physics, we'd work in newtons, is what we would work on. So you may hear people talk about newtons, and that's the same as 1 kilogram as meters per second squared, hasn't it?
Right, yeah, meters.
Okay. We, however, because of the fact that we're going to be working with typically construction concepts in America, our forces are going to be in pound forces. Okay? Where here we're just doing our weight, which is our mass times speed of gravity. Okay? So when you think back to materials 1, when we broke the concrete cylinder, the pounds of force that the cylinder resisted before it failed, that's what we're talking about here. Okay? Questions on that? How we're going to figure that out? Okay. So we need to be aware of the 3 major properties of a force. It's all fine and good, at least in these first couple of weeks, we're going to talk about this concept very theoretically, so we can understand axial forces, so we can understand shear, so we can understand buckling. But once we get through the theoretical, then we're going to move into actually investigating what's going on out in the real world. Okay, so we have to understand how is a force going to operate in three-dimensional space. So what is it going to need to have? Three things that we're looking for. It's on the terminology quiz, right?
Magnitude.
Magnitude,
Sense.
sense,
Line of action.
and a line of action. What do these things mean? What does a magnitude mean? Is 50 bigger than 10? That's our magnitude, right? So that's how much is that force applied. Okay? What about a sense? Sight? Smell? Right? Is that what we're talking about here? What are we talking about when we're talking about a sense for a force? Yep. It's going to be the direction this thing is acting. And how about a line of action?
What plane it's on?
Yeah. Very good. Okay, so why that's important to understand, I mean, it's not going to make a whole lot of sense up here when I'm drawing it in 2 dimensions, right? But when you think about it on a job site, when you think about it as a series of elements interacting together, it will start to make sense, okay? So if I say that I have a 50-pound force, its sense is running this way, right? Its line of action is running along that space. If I also have a 10-pound force, different magnitude, different sense, one could kind of argue. We don't know how it's sitting in this direction, right? It looks like same line of action because I don't know how to draw in 3 dimensions on that board. It would make my mind hurt also. So, but based on the limitations of the board, same line of action, right? But different senses. They're operating in different dimensions. Why this is important for us to understand, think about things like if we're erecting a steel building. We need to know, as we start connecting members of these forces together, how are these forces going to interact with each other? Okay? Also think about things like a crane. If it is a windy day, and we're going to do a pick with a crane where we need to overextend the boom, we may need to look at a chart to see, is our crane going to tip over and get us on the evening news? Okay, so there's all sorts of safety aspects that go into understanding how these forces interact with each other. If we can't keep our forces in static equilibrium, things are going to change from how they were when we began whatever it is that we're looking at. Okay? Does that make sense conceptually to everybody, why this is important to us? Okay. Let's see. We talked about static equilibrium there. Everybody good if I take this stuff away now? Kevin, would you do me a favor? Is that thing still recording?
Yeah.
Okay, thank you. So one of the first things that you're going to look at is how do we deal with components in combination with forces? Okay, and what we're often interested in, a concept called the resultant. Anybody remember what the resultant means? We're talking about combining forces.
Reminds me of basketball courses, you know, something.
Yeah, exactly. Okay, so think about, we'll use a steel project again. So think about if we have a poorly drawn steel column, right? And as this column sits in space, let's say that we've got a 3-story building that we're looking at. And we can't see it too well from here, but we've got beams projecting out into the studio behind us. Don't worry, we installed them in such a way that nobody's in any danger. Okay? Don't go far enough into the road. But we have 3 nodes coming into the system. So what the structural engineer is concerned about is how are all the loads being transmitted by this building coming into this column, into all these nodes, then being transmitted down into the ground into whatever foundation system that we have. Maybe it's a strip foundation, okay? So we want to make sure that as these forces come down, we have enough resistance in our foundation so this thing doesn't just get torn right out of the ground. Okay? So that as these steel members deflect, once we load it up with whatever we're going to occupy this building with, desks for offices and people who work with them. Maybe it's a medical center, right? As these start to deflect and change how our forces align, that isn't going to cause any differences, potentially cause buckling of that steel column. Okay, so all the sorts of things that we have to take into account. We're also interested in, when we make this connection, whether we're welding it, whether we're bolting it on site, is our connection strong enough that when we apply forces due to live and dead loading, we don't just shear this beam right off at that location. Okay? The building itself will do all right because this column will stay in place, but the people occupying that floor aren't going to be too happy, right? So those are all the things that need to be taken into account. And how we look at that is we combine those forces and turn them into a result. Okay, so as part of the first homework that you have, we'll look at some very simple cases where we're going to combine 2 forces into a single result. Okay? So the first one that we'll look at, and I'll be drawing freehand, so you have to excuse my inability to draw completely straight. Okay? What I would recommend, if you don't get a ruler of some sort, what I do for the keys that you have for this class, I think I was smart enough to remember to put it in here. There it is. I just got a little engineer scale like this, right? So it's got 6 different scales on it. So depending on how much you need. You can change the scale on your sheet of paper. It helps everything work much more smoothly. And the reason being is we want to make sure when we're drawing our 100-pound force, and then we draw our 50-pound force, our 100-pound force is twice as long as our 50-pound force because it has twice the magnitude. Okay? That's going to allow you to make sure that you can place this resultant in the proper location. Okay? And set that marker down. We can look at this visually as where our resultant will be located. By just completing a force parallelogram, and I know this thing isn't parallel, but show disbelief in the reality of my drawing, right? Okay, so imagine that these are parallel, making 4 right angles. Okay, so your resultant force is going to be the force that joins that segment. Eek. That's not good, sorry. A little better. Okay? So, what do we know now about this shape? It's not a trick question. It's a triangle, right? Which is why I had you do some initial math problems on triangle math, right? Okay, so what can we determine using what we know? What could we figure out if we wanted to?
Just 180 degrees each.
If we had these 3 angles are going to be 180 degrees, yep. Do we know what the magnitude of this leg is?
Yeah.
Do we know what the magnitude of this leg is?
Pythagorean's theorem.
Yeah, we know opposite in this case, and we don't know.
Okay. So if we call this, say R, for a resultant, that's what 4 years of engineering school does for you. All types of creativity. Okay? So if we call that a resultant, how do we determine the magnitude of that force?
Basically equals B squared equals C squared.
R squared is going to equal 50 squared plus 100 squared, right? Okay? Who wants to be the brave soul to figure that out for us? Without just grabbing my sheet of paper off my desk.
$111.8.
111.8. We'll call it 112 pounds. Does that work for everybody? Because we started here, didn't have any decimal places, so we'll maintain the same level of precision. Okay? Okay, so that's good for us to know. Okay, so maybe we'll consider we've got some sort of node here. We've got some sort of column, right? And we know that we have a girder coming out that's pulling on the thing at 100 pounds, and we have another girder pulling out at 50 pounds. We want to make sure how much resistive force are we going to have to keep that column in place. Okay? So now we know the magnitude of this thing, right? But we also need to know the sense in the line of action. Okay? We know the line of action. It's moving in this direction. But we, at this point, have no idea what its sense is. Okay? How it's operating in the plane. When you are doing your homework assignments, it does not matter to me if you orient from the vertical